Welcome. I'm Barbara Giunti, and today I'm going to talk about an introduction to topological data analysis via its industrial application. I'm an assistant professor at SUNY University at Albany, and I'm very happily here in Stockholm as a SEC scholar for Digital Future. So thank you, Digital Future, for allowing me to come here and present my work. Okay, so first let me give you an introduction of what is topology in general. Most of the math in this talk is going to be very end-wavy because I want you to get the idea, but not be bored by the details. But if you have more questions, feel free to contact me or any of the people that I'm going to mention in this talk. So topology is a branch of math that studies the property of objects that remain unchanged or that change under continuous transformation. What is a continuous transformation? Well, for example, you can imagine this that I depicted in this picture. What you are doing is you're sort of stretching your grid so you can see that all the mutual angles are still the same, and we still have 90 degrees, but the distances between 2 points change it. So the lengths are not preserved. Another very simple continuous deformation is I have an object and I needed to rescale it to a bigger or a smaller size. Something more funky is represented in this GIF. So here you can see a donut that transforms into a mug. Now, you imagine your object made of like a Play-Doh or clay, and then you can stretch it and do things with it, but you cannot break it or glue it back together. So you can see here that the property that really stays is this sort of loop or this sort of hole that both shapes have. We're going to come back to it in a second, but this is just the general picture of what topology is. Now, this is interesting, of course, but why should we care, right? Especially in the optic of industry. Why do we care about this abstract nonsense? Well, topology is a very mathematical concept, very abstract, but the answer to this question is actually very practical and engineering. It works really well. And when I say really well, is that I also have a way to classify or to state what it means to work really well in the form of a database. This is called a donut in the honor of a very classically used shape in homology, in topology also, which is a database of original non-theoretical uses of topology. Non-theoretical here being the key, especially for predictioner, because each of these papers, and we have over 475, or 475 to the date, are on practical uses, so real world example of data that have been analyzed with topology. 32 in industry, which is a possibly good percentage, but I would like to see it growing, which is one of the reasons why I'm presenting this talk. And each of the entries labeled by the area of application. Usually, for example, let's say that you have something in industry, and you also want to be a little bit more precise. You want to know that it is about manufacturing. Well, we have the tag industry, semicolon, manufacturing, so you can navigate the level of generality that you want. Mathematical tools, so not just the topology ones that I'm going to present in a moment, but also the other ones that you will be using. In your analysis somewhere, did you use also PCA or Fourier analysis? Well, this is labeled there. Input type, we're going to discuss input type in a couple of slides, but the idea is that I want to know how exactly to use the data that I have. And to do so, maybe you want to check what other people have done when they have the similar type of input, like an image or time series, for example. Finally, last but not least, the degree of novelty. Degree of novelty means that with topological method, you can do things, you can analyze data in a way that you couldn't before. And couldn't means that maybe topology give you an edge over the size of the input. You can do a much bigger size. Or at an earlier stage, for example, in an application that we have in medicine, you can catch some diseases at an earlier stage of the development to increasing the chances of recovery. Or also, simply but crucially, the input type, the data are easier to get. In another application, again in medicine, PDA so topological data analysis can give you an answer from a CT scan and not from a biopsy, which was the method known before. So this is what we mean by innovate, and we have 77%, sorry, 77, not 77%, that would be great, 77 entries out of 475 that are labeled innovate, and very interestingly, 10 of them are in industry, which means 1/3 of all the applications that we have in industry are innovative, so you can do something that you couldn't before. Now, let me just quickly show you this data set. So it looked like a search engine, and this is what we wanted to have. And if you want, for example, to have industry and innovate, so you can see here that you can also combine keywords in your search with and or and XOR, etc. So let's say I want to have industry. So the tag industry means that the area of application is industry. And I want also to have the tag innovate. And then you say search. And here we are. We have 10 of them. And you can check what are the other tags. You have a link to the file. You can export the citation for citing it in your paper or the other work. So I think this is a great tool, and I hope you will find it useful. Now let's go back to the presentation. Okay, there are additional information that I forgot to say, such as what are the software that you've been using, what are the data set, so that you can either use the same data set and compare the analysis and the result, which is very important, or simply go to the data, to the software, which usually are open source in our work, and simply use them too. Okay, so what is the overview of what I'm going to talk about today? I'm going to first present the general TDA pipeline. So how does it work in general data analysis? And then I'm going to present three methods: Mapper, which is a clustering algorithm; thesis and Homology, which is an extract topological feature; and Umap, which is a dimensionality reduction method. For each of them, I'm going to present briefly how they work. I'm going to showcase their functionality with an example coming from industry, and then I'm going to summarize the pro and con of them. Then I'm going to provide a general comparison and some future direction for what you can do with what we have now. Okay, and this is based on a preprint that is available on the archive. So this overview of topological data method, topological data analysis method in industry, you can find it here if you want more references. Okay, so what is the general TDA pipeline? You start with data, you turn it into a combinatorial object, and from this combinatorial object, you extract information. So let me go a little bit more in detail into each of these stuff. What are data? Well, actually, TDA methods are pretty agnostic about where your data come from. We don't really care, as long as it looks like or it enters in a shape that the computer can analyze. And there are several shapes. So actually, for example, 2D or 3D images, those are fine. Time series, point clouds. We have a graph or even text. We have some application with just simple log test of what the work was doing. So TDA doesn't really care where your data come from. You need this information, of course, for understanding or for doing a meaningful data analysis, but then the software will not really need to know all this information from the specific application, which is very good. The combinatorial object, there are mostly two types: graph, which I'm not going to define much because I assume that many people are familiar with them. Otherwise, if you're not, the very brief and complete description is basically that you have vertices and edges between them. Or, for one of the methods, filtered simplicial complexes. Now, I assume here that people are less familiar with simplicial complexes and filtered simplicial complexes, so I'm going to give a proper definition later on. Extract information. How? Well, there are basically two ways. One is direct interpretation. So I put my data in this pipeline and I get out some invariant, some information, some descriptor, and I simply go back to my expert and ask them, okay, I have this feature, what does it mean for you? So you can directly interpret. Or all the methods that I'm going to talk about, you can vectorize them or and then feed them directly to a machine learning pipeline. So topological data analysis method they may compete with some other data analysis method, but they can also be put together so you can have just more information in one analysis. Okay, let's start with the first method, which is mapper. This is a clustering algorithm. It reduces the input dimension by mapping the data into a graph that looks like the one I'm showcasing here from the very first paper about mapper, that is references below. Each vertex represents a cluster. An edge between two vertices means that two clusters share some element. And the topological or geometrical property that we are interested in are kinetic components, like pieces of the graph, loops, and flares. For example, here you can see that we have a loop here, and we have some flares, which means that those are a series of clusters that are connected one to the other, but they are not really connected with the rest. So you can see, for example, that this cluster is very central somehow because it's connected to several other clusters, right? While this cluster over here is just connected with one of them. So you can search and see, okay, this flare, you come back to the data and say, oh, look, these are things that have more or less the same behavior or they are linked somehow. So what is the mapper pipeline? Let me first draw a picture because then you can have it clearly in your mind and then go to the math. So you have the data and you take a function that is usually called a filter function or a length function, and you map your data to R. Technically, you don't really need to map it to R, but this is already rich enough to give all the information or most of the information. So you can map it into something more complicated like Rn or a circle or a sphere, but why complicate your life when R is simply already working? Okay, now, and this function could be, is typically something like PCA or some other kind of orthogonal projection, so something sort of easy. You can choose freely. Then we cover the image of F with interval. So we go here in R, and then you can see that I put some interval, some bars here. Then what we do is we take the pre-image. So we go back. For example, I take the purple one, and I see what are all the points in my data that are mapped into the purple interval. Well, this one, this one, this one, this one, and this one. So here, this is exactly what happens, right? Okay, and then I'm gonna cluster them. So I'm choosing a clustering algorithm, and I say, okay, these 2 points goes together, these 2 points goes together, this point stays alone. Then from here, I build a graph. Each vertex is a cluster, and then I put an edge when there are two clusters that share some point. For example, here, I have this cluster that is sharing some point with this cluster, which means that I'm gonna put an edge here between the blue and the purple one. Okay. Now, this is basically the same picture, but here I'm highlighting where are the points in which you have to make a choice. You expert who wants to apply TDA method. Well, you need to choose the filter function, the cover, and the clustering algorithm. And the problem with applying mapper is that these choices, there aren't many mathematical criterion that force you to make some choices, which means that you have a lot of freedom, which is actually not super good because your final analysis may depend a lot on what you choose. So you need to tread carefully. Okay, let's study an industrial application, first of all. The reference for this paper is below. The goal here is to develop a demand forecasting system for electric components. So you have electric components and their demand, which means that you have your input type is a time series over time, with also the feature of each electric component. And what you do is you first apply mapper on a subset of the input, because you're going to have, I don't know, 100 or thousands of electronic components, and you just want to start with a smaller amount. This is going to call it the training set. For the training set, we manually and painfully search what is the best forecasting model. Okay, so here I have my cluster. That is, this picture comes from the paper. And for each cluster, I say, okay, look, this is best. So all the electronic components that are clustered here, they are forecast best with this forecasting model or this other forecasting model, etc., etc. Okay, so this part is very expensive, but I'm doing it only for a subset of elements in the graph. And then what I do is that I come back to my huge set of initial electronic component, and then I map it to the graph, one at a time, only the one that I need. And I check where in the graph, where in the final graph this goes with a k nearest neighbor. And then with this operation is not so expensive as comparing all the possible forecasting model. But now that I know where or close to what in the graph my electronic component will be, then I can say, oh, look, I'm going to just check what is the closest cluster. And the best forecasting model is going to be the same, because this electronic component behaves in the same way as the one of this cluster. So this is the idea. Which is much cheaper than just recomputing all the possible forecasting model for the whole set of electronic components. So let me give a summary of mapper. This is a cluster-based dimensionality reduction method. What is good about it is that it's parallelizable, because the clustering algorithm can be applied only on a single pre-image, which means a much smaller part of your input. And then you can do it all the pre-image in parallel. So it's pretty good. There are many available implementations that are usually open source, but let me be clear, there is a company that has patented the original mapper, which means that the best performing is it, and you need to compare or be aware of it. The main obstacle for using mapper properly, even if mapper is hugely successful, is finding the correct choices of filter function, cover, and clustering, as I mentioned before. Let me explain what happened. In the graph that you can see now on the screen, the author made a choice of having 4 overlapping intervals. So the covering is 4 intervals. This is the graph when you have 3 covering intervals. So you can see that the circle disappears and there are many fewer branches, which means that I can still see the 2 flares, which probably indicated that those are a strong behavior. But some of the features that I was capturing are no longer there. This means that it depends, your analysis is not really robust against the different choices of cover and clustering and filter function. So you need to be careful. That's why this is the main obstacle. Okay, let's go to the second one, thesis and homology. The key idea is that when you are doing some data analysis, you have to choose some threshold. For example, when you binarize an image, or when you say, okay, I'm taking a certain length of my, time series, or I'm taking, some parameter, you need to choose it. And the point is, you don't want to do that, because maybe when you choose a slightly different value for your binarization or for your threshold, you have big difference in the output. So precision homology wants to overcome that. And it is a feature structure, so it's not a dimensionality reduction method, it's not a clustering method. It allows you multi-scale analysis, and this is very connected with the fact that you don't need to choose a threshold because you will analyze all thresholds at once. Since you don't need to be there and choose, this really helps with automatization, and we're going to see it in the application that I'm presenting. It is both directly interpretable and it can be fed to a machine learning pipeline or other method. This is more or less the pipeline. You have your data, you need to choose a parameter. We're going to come back in a second about that. And you obtain a filtration. And this filtration is your combinatorial object. From it, you get a barcode. And the barcode can be, as I said, either interpreted directly or vectorized for machine learning, for example. Persistent homology uses simplicial complexes, which means that now we need a little bit of math. I promise I have very few slides with mathematical content, so bear with me, but just shortly. The rough idea of simplicial complexes is that this is a higher dimensional version of graph. In a graph, I can have a relation between two vertices by saying that they have an edge between them. In a simplicial complex, I can say that there are three vertices in relation with each other because there is a triangle between them, or a tetrahedron between four vertices, etc. The rule here is just, if I have a tetrahedron, then I also have all of this triangle and all of these edges and all of these vertices. So for example, here, three cases of simplicial complexes. The first one is also a graph. The second one is also a graph. But the third one is not a graph, because the third one, this is a tetrahedron. It has four vertices, and then all the possible edges between the vertices and all the possible triangle in here, but not, sorry, it's not really a tetrahedron because it's not filled in. So there is a cavity, it's like a ball, an empty ball. What is a filtration? Well, this is actually very easy. It's a nested sequence of simplicial complexes. And nested, it just means that one is included in the other. So if I put this arrow, then my three simplicial complexes just become one filtration. Because you can see that this is inside this one, and this one is inside this one. Very importantly, those are stored in my computer as matrices, which means that the operation that they're going to do computationally are mostly like linear algebra operation of adding and subtracting columns, swapping columns, or the same thing with rows, which also hint at the main obstacle to applying persistent homology. We are not really good at dealing with huge matrices and operation with them. We run into computational issues there, right? Which means that persistent homology is very good for a slightly smaller input than what Mapper and Umap can deal with. What is homology in the persistent homology world? It is an n-dimensional holes in the simplicial complex. This is a hand-wavy layman interpretation of what is homology. This interpretation immediately fails in dimension 0 because 0 is always a little weird. This simplicial complex here has two zero-dimensional holes. A zero-dimensional hole, you can imagine as the white part between the pieces. So it basically says that you have two pieces. You have two parts that surround your two pieces. It's easier in a higher dimension. This simplicial complex has one-dimensional hole, which is this loop. It's like a circle. So you can imagine that you can poke in, and this is a hole. And simplicial complex here has a two-dimensional hole because I have a cavity inside. So everything is closed, but inside is empty, and this is a two-dimensional hole. Now, I cannot show you what is a three-dimensional hole, but you can imagine that it's just the same thing higher up. Okay. So the persistent homology is the homology of a filtration, simply put. Okay, so what does it mean? It means that here I have two pieces, and here I have just one piece. So I'm going to record this as, I'm going to record it as a bar, and I'm going to come back to it in a second. But first, let me just explain you how you get from data to filtrations. There are many ways, call it alpha, Vietoris-Rip, check filtration, and they depend on the input format and the specific requirements that you have. So you have a little bit of choice here, not too much, which is actually good for data analysis, because then you're forced to use specific methods that usually are already in the literature. Even if this choice the one that you have does affect computation, for example, I would strongly suggest you to use a alpha complex anytime you can. It makes sense. Instead of a Vietoris strips, but the Vietoris strips are the one that we can use in higher ambient dimension, where alpha we only have in lower ambient dimension, meaningfully. As I said, the computation is basically Gaussian reduction, which means column operation, on big matrices. So basically the choice of the filtration impacted the size of the matrices, which then impacted the computation. So this is where it goes. Okay, so what do? We start with data. We construct a filtration, and here I just gave you another example to compute a filtration, which is you have a point cloud, and you make balls growing for each point. And when 2 balls grow, you put an edge. And when 3 balls grow, intersect together, you put a triangle. And this will give you your filtration. Here I just put the ball growing for giving you an idea. What is the information that we extract? This is the homology of a filtration, right? This is the definition from the previous slide. Well, here, these purple bars are the one telling me the pieces, so the 0 holes that I have. Here, I have a lot of pieces because my balls haven't grown yet, so they are not touching each other yet, right? So I have a lot of bars at this moment, but here you can see that all of them basically end but one piece because all of these balls are touching each other, which means that I have at the end just one piece because they are all connected. Good. At a certain point, these balls start to touch each other, right? Here they are almost, but not yet. And here they are definitely touching each other, which means that I have these 2 red bars that are telling me that I have, each of them represent the lifespan of a one-dimensional cycle. So the one-dimensional whole. And you can see that at a certain point, they are both born. See, I have both ones. And these get filled up before this one. So this bar ends earlier. And then at a certain point, they just get all filled in. So the information that my data gives me back, or my data analysis gives me back, is that I have a series of bars, or short bars in dimension 0, zero-dimensional bars. And at a certain point, I have just one forever. And for a long period of threshold, for a long value of threshold, I have 2 cycles. So what I can back and say, let's say that I wanted to recognize, I sample some writing, and then I want to recognize what are the letters. Here I can tell you, look, this is a letter or a number that has for a long time, which means that significantly has 2 circles. And you can say, okay, that may be a B or an 8, but it's certainly not an I. So this is how you can analyze it. What is nice, very nice about this pipeline is that we can define a meaningful distance on data and a meaningful distance on the barcode, which is the name that we give, very intuitive name that we give to this invariant. This is output. And what is good is that the distance of the data is greater or equal than the distance on the barcode, which means that if your data changes slightly, let's say you have an error in measurement, or the machines that are taking the measurement, they have a little bit of leeway, right? This difference, it will be bigger than the difference of the output that you compute, of the 2 barcodes that you compute, which means that the analysis is robust with respect to small perturbation, which is very good because it means that the information you extract is trustworthy. Let's check an industrial application. What we want to do here in the paper that I'm referencing on the side is identify the onset of severe slag flow in offshore petroleum production. So not really green, but it's very nice. This application, I like it a lot because it's showcasing all the potential of persistent homology. So what we have here, we have this offshore petroleum production, where of course clearly we want to have as fewer people as possible because it's a very harsh environment, and we want to do the least maintenance possible because it's very hard to get there. Right? And the severe slag flow is when you have so when the flow of your petroleum is slagging, which means that you have something that is denser and then lighter, and then it goes on, and put a different level of pressure on the pipes, which is not good. It increases the need of maintenance. My input are going to be, again, time series. Time of the pressure sensor in subsea oil wells. So which means that here, down there are pressure sensors that are just recording what's happening here. Look, here, the pressure is more or less constant, and then I have some spike, and then it comes back normal. This is the picture of what happened. I have the pipeline, I have the pipe, and then at a certain point, I have this log. So it's something that is much denser than is preventing the flow to go. And then when it finally managed, the pressure is so high that is basically the fluid explode down the pipe, which is not good. But what is very nice is that this analysis is independent on the industrial asset. So it doesn't care about what is the shape of your pipe or what they look like. It doesn't matter. The fluid characteristics, so you don't really need to have petroleum or the thermodynamic. So this is very good. You just need this time series, which is very good. The workflow is that first, very classical when you have when you want to use persistent homology with time series, you embed the time series with a Jenkins embedding. And here on the left, you can see this is the embedding when you have when you don't have slag flow, severe slag flow. And here is when you have it. So what happened with the slag flow is that the pressure pipe, it will have a spike and then it goes down, and then this happen again, okay? Which means that when we embed it, we can see this circle behavior. And I just presented you a great method to understand when something has a circle in it, which is homology. So it is already intuitively pretty great. If you want to find out periodicity in any of time series that you have, you can use persistent homology. Then you compute the persistent diagram, which is, I put it here so you have both picture. You can describe the output as a barcode or as a persistent diagram. Those are the same thing. You can read the bar like this. This is the birth of the bar, and this is the death of the bar. So the higher here, the longest the bar will be. The closer to the diagonal, the shorter the bars will be. So this is two ways to show the exact same things. And this is the persistent diagram of what happened on the left. And you can see that there are very short-lived cycles. So here is 0.1 and here is 0.1. Okay. This is the persistent diagram of what happened on the right. And you can see up here, I have a point at H1, which is a one-dimensional hole. I have a long-lasting circle, which is exactly the feature that tells me that there is a slag flow, there is a cycle, there is periodicity in my time series. Now I check the topological feature of the severe slag flow, which is if detected, I can mitigate it. So what it means that what I'm describing you is actually fully automatized. You don't need to have a person checking the data and say, oh, look, this is about to happen. Let me mitigate. Let me change the pressure in the pipes down there. No, you just need to train your computer to recognize that when you have something up here, you have a slag flow, act immediately. So it is fully automatized. Summary. This is high-dimensional topological information. It's great for automatized tasks. It is stable with respect to at least some noise. and it has many open sources implementation. No company on it yet. Drawback, of course, you have medium small data. So up to 10,000 points, we do quite well. More than that, yeah. 10,000 points is already borderline, depends on the filtration. If you have 1,000 points, then I'm pretty sure you can use any method, then it's fine. Mostly one parameter. What does it mean? Well, here I told you that you can avoid choosing the threshold, but it's in just one direction, right? There was one value that was changing. In one case, it was just the pressure, for example. But what if you have things that changes in the sense that you have different pressure and you have, I don't know, different temperature? Why don't you can analyze both of them, right? Changing at the same time. So you don't have something that changes in one dimension, you have something that changes in 2 dimensions. We are getting there. We are mathematicians, we are slightly slower than industrial probably need. So for now, multi-parameter persistent, which is actively studied by many groups, and we have also several algorithms and several methods to extract information, so you can use it, but it doesn't yet have a clear comprehensive theory as the one parameter persistent that I presented now. You don't have a barcode at the end, for example. You have something much more complicated. And possibly you need to choose depending on what data or what is your specific analysis that you're doing, which is why I didn't present it yet. But if the need arises, keep in mind that we can do something, okay? Last but not least, uniform manifold approximation and projection, which is Umap, the initial. First, let me give you the pipeline. You start with the data, you choose a number of neighbors, and then you create a high-dimensional weighted graph in which you are recording all the information about the distance that you care. Then so basically all your effort is in creating this graph, even if it lives in high dimension, we don't care, but this graph is a good approximation of what we started with. Now that we have a graph which is much more manageable, we turn it into a combinatorial object that it is a low dimension weighted graph. And then we can interpret it. Actually, here the interpretation is not on the nose. Umap is very hard, or I'm not aware of any way to interpret it directly, but you can use it together with other dimensional. So it's like this is a dimensionality reduction method, which means that you can just use it for further analysis, as we will see in the application. Let's say that you start with your manifold and you have points in it. And you made a choice. In this case, I made a choice of k equal 2 for studying the neighbor. So I'm taking xi, and I'm studying its 2 closest neighbors, which in this case are xj and xh. Okay, let me just copy it in here for having it more precisely. Okay, what I want to do now is approximate the geodetic distance from xi to xj and xh. Okay? And I'm going to do it is for all the points on my manifold, or for all the sample in my manifold that I'm interested in. Now, what is the result of this thing? The result of these things is a little weird in the sense that when I analyze xi, I obtain different things of when I analyze xj. For example, the distance approximated from xj may not be the same that I approximated from xi. It may even not be there because I choose in the 2 closest neighbor of xj, and xi may not be the closest neighbor of xj. Okay? I could have 2 other points here that are closer to xj than what xi is. Also, when I'm studying xj, I have I have no information between what is the mutual distance between xh and xj. Okay, so at the end, I have a set of distances that is approximating, but is a fuzzy set. Fuzzy structure are a very abstract mathematical concept, but the interpretation is quite easy. A fuzzy set is a way to weight the membership of an element to a set. So you don't say the binary option, this element is or is not in this set, you have a number or a value that says this element is 50% in this set, or with 80% probability it is in this set, with one weight equal 1 is in this set. Okay, so I can use this to collect my distances, the one they approximated, and the distance is going to be the value of this fuzziness. Okay? Then I'm going to use a directed graph to smooth these inconsistencies of having one direction and the other direction of different values. And finally, this directed graph is the way in which I obtain my weighted undirected graph. And from there, you can use different methods for just mapping and projecting your graph into a lower ambient dimension. What is really nice is that since the distances are calculated locally and they are approximated and they are changing, this is a great tool against the curse of dimensionality when you have a high ambient dimension, which is pretty good. So let's look at an industrial application. The goal is that I want to identify systematic defect in system level tests. So I'm gonna system level tests are a way to check if my if the parts that I have in my manufacturing component are working or not. But it's not great for diagnostic, which means it tells you that you have a problem, but it doesn't really tell you where the problem is or when it occurs. So you want to extract this information from the system level set that you did. And the input is a point cloud, which are the system level set test report that are buffer sort and final data test. And this really means nothing to me as a mathematician, but I'm expected to be more meaningful for you from industry. Okay, I'm gonna just use the pipeline that it is in the paper because it's very good. So I start with my point cloud and I use Umap to reduce the ambient dimension. Now I have a low dimensional embedding and I can use a clustering method like HDB scan. And then with my clustering, I can create a decision tree and say that, look, if this happens, then this is the component that failed. If this happened at this time, then you need to go there because it is other component that fails, etc. So now we have a tool for diagnosis. I expect you to have some question like, why not using directly HDB scan? Well, because it's terrible when the ambient dimension is high enough. You will have just one bubble of cloud, which is not great. So you first reduce it, and then you can use your preferred clustering method. Why not use order dimensionality reduction method? The reason here is just they tested in this paper, and Umap works much better. So if you use like PCA, this is the clustering you obtain, not informative. If you use another method like TSNE, you can cluster, possibly, but not perfect. But look how nicely clustered things are when you use Umap. So maybe Umap is not the tool that you're going to use for one specific analysis, but please keep it in mind because maybe it is exactly the right tool that you didn't know you could use. So as a summary, Umap is a dimensionality reduction method, is robust against the curse of dimensionality. It's suitable for large data sets. This is one of the strongest points. It scales very well with the size. It has open source implementation. The drawbacks may be possibly that the output may be further analyzed, so it's not enough to have it all of them. It has this hyperparameter tuning, so the choice is not robust against choosing 3 nearest neighbor, 2 nearest neighbor, 5 nearest neighbors, etc. So you need to be careful. Okay, now let me give a general summary of what I presented now. There are 3 methods. Mapper, which is a clustering method that is parallelizable but requires not intuitive choices. Umap, which is a dimensionality reduction method which is resistant against the curse of dimensionality, is suitable for large inputs but requires some hyperparameter tuning. And persistent homology, which extract high-dimensional topological features, so information that usually, I mean, I'm not aware of any other method that can extract this type of information. It is automatizable or faster automatization. It unfortunately requires medium small input, and for now, the best use is one parameter, even if, let me repeat it once more, if you require multiple parameters, contact some of us, because maybe we already have the method we need for you. Those are two-dimensionality reduction methods. Both of them, both mapper and persistent homology, allows for direct interpretation, and all of them are machine learning compatible, which means that you don't need to give up on your favorite data analysis method, if machine learning, for example, is one of them. You can just do both things together and extract better information. What I would like you to take home from this seminar is that DA is great. It's amazing. You should consider it. Can be used alone or in combination with other technique. It has many open source implementation, which I feel is like big plus. It has a solid mathematical background, and it can extract information that no other method can. Maybe not always, but it can. So it may really be something that you needed. And I think it's currently underutilized in industry, so you can have a big advantage of starting using it. It is a very active area of research, which means that, okay, so for example, Albany, which is my affiliation, has a big center. We have 4 professors, 2 assistant professors, and 2 associate professors. But KTH, too. There are Martina Scolomiero and Wojciech Kachuski and several postdoc and PhD students. So you don't need to come. I'm happy to either to come back to Stockholm again or to welcome you at Albany. But you can also just knock the door of your neighbor at KTH and have great answer for TDA method. If you don't find what you need on the shelves, we are happy to collaborate. We are very, very eager to motivate our mathematical abstract nonsense with actual need. So I think we should collaborate more. There should be more partnership. And usually TDA is a pretty open community. So I hope you will be welcome too. And with this, I end my talk. I remain available for any question that you may have. Please contact me offline with email, etc., or in Stockholm, as long as I'm there. And yes, have a nice day.